everyone, this is the video lecture for class 19 of PH 125, and today we're going to be talking about impulse and momentum. So this is the start of a new chapter. We're going to be talking all about linear momentum, impulse, and collisions throughout this entire chapter. So let's get started with our definition of momentum, and we're going to start actually by looking at Newton's second law. So just a quick reminder, we know that Newton's second law tells us that the net force acting on an object, which is equal to the mass of the object multiplied by the net acceleration of the object, it's also equal to the sum of the forces acting on the object. Okay, so we can rewrite this then in terms of the change in velocity of our object, because we remember that acceleration is really just the rate of change of velocity. So in other words, it's just delta v over delta t. And so plugging in that the acceleration is really delta v divided by delta t, we get F net equals m times delta v divided by delta t. Okay, now we want to keep this in mind, but we're going to define a new quantity, which we call linear momentum. So linear momentum has the vector symbol p. So you can see it is a vector. It has both magnitude and direction. And so that means it's going to be represented with arrows, right? And we're going to have to think about vector components here. So we're going back to that. I'm sorry, I know it's coming back. But so we're always going to want to be thinking about x and y components of the momentum. Momentum is defined to just be mass times velocity, so m times v. Mass is a scalar quantity, it doesn't have direction, and so remember when you multiply a scalar by a vector, your new vector quantity, so here p, is going to have the same direction as the old vector quantity, so here that's v. So in other words, p and v are going to be in the same direction, so if you know the direction of the velocity, you know the direction of the momentum, and they're just directly proportional to each other, so we have p equals m times v. Okay. So looking at this definition, P equals m times v, we get units of kilograms for mass, meters per second for velocity. Doesn't really have a special name. It doesn't at all have a special name. It's just kilograms, meters per second for the units of momentum. Okay, and so it turns out that momentum is a really useful quantity in measuring the motion of an object. Sometimes, it's not sufficient to know about its velocity. We want to know about a quantity that's related to both mass and velocity, and so momentum ends up being really convenient for that. Okay, and so then it turns out that it's related to the force that an object could exert on another object during a collision, or alternatively, you can think of the momentum as being related to the force that's required to change the motion of a particular object. Okay, and so how is this relationship to force coming about? Well, we can think about it by looking right back at this Newton's second law that we rewrote in terms of a change in velocity divided by change in time. All right, so looking at the definition of momentum, P, we would say that delta P would be equal to P final minus P initial, right? So anytime we have that delta, it's always change in, and so that's always final minus initial. So looking at P equals m times v, that would be equal to m final v final minus m initial v initial. Okay. So in general, actually, the mass of an object won't be changing. So usually, even in a collision, an object's mass will be constant. And so m final and m initial will generally be the same. And so we get m times v final minus v initial. All right, and so then that term in parentheses is really just delta v. And so in other words, we get delta p equals m times delta v. And so then looking at the equation that I have the star by, so our Newton's second law, I see right here in the numerator, I have m times delta v. So really that's just delta p. And so then the net force acting on an object is really the change in momentum with respect to time. So in other words, delta p over delta t. So this net force acting on an object, it causes a change in the object's momentum, delta p over delta t. Okay, and so actually this is how Newton wrote his own second law. So I know we learned it F net equals ma net, but if you go back and read like his original manuscripts, which I'm sure you guys are all just dying to do, he wrote his second law in terms of F net equals delta p over delta t. Sometimes this is referred to as the momentum principle. Okay. All right, and so now we're just going to do a quick little review of how we could get to the work and energy theorem from Newton's second law, and then we're going to take a similar method to compare momentum to this thing called impulse, which I told you we'd be talking about today. So let's start with work and energy, starting with Newton's second law. Specifically, we're just going to look at the components of Newton's second law in the x direction. Okay, and so then what we can do is just imagine multiplying both sides of this equation by some displacement delta x. So if I do that, then what we can see here is on the right-hand side, I have a term a net x times delta x. So you might remember from the equations of motion with constant acceleration that we defined a net x times delta x to be equal to 1/2 vx squared minus v naught x squared. So really, the equation on your equation sheet probably looks a little different. Remember, this is the equation that doesn't involve time, but I've just rearranged it here so that I have something with a net x delta x on the left-hand side, and then what I can do is I can replace a net x delta x in my equation with what I have on the right-hand side here. So 1/2 vx squared minus v naught x squared. All right, and so that's what I've done on this third line of the equation here. I've just replaced a net x delta x with 1/2 vx squared minus 1/2 v naught x squared. I've distributed the 1/2 inside the parentheses. Okay, and so now looking at the right-hand side, I have m 1/2 vx squared minus m, if I distribute the m, 1/2 v naught x squared. And so really remember that kinetic energy is 1/2 mv squared, and so really the right-hand side is just change in kinetic energy. The left-hand side, we have net force in the x direction multiplied by displacement in the x direction. So remember we talked about work being force times displacement, where really it's the component of the force that's in the same direction as the displacement. And so then F net x times delta x is really just the work done. And then the right-hand side is the change in kinetic energy. And so I get W total is equal to the change in kinetic energy. And this was the work kinetic energy theorem. Okay. All right, and so now let's use a similar method to come up with a relationship between impulse and momentum. Okay, we're going to start again with Newton's second law, and we're just looking at x components for simplicity. All right, and now instead of multiplying by some displacement delta x, let's multiply by some change in time delta t. And you just, as long as you multiply both sides of an equation by the same thing, that's allowed, right? So we've just kind of arbitrarily seeming, but I promise there's a point to it. We've multiplied both sides by delta t. Okay, and now I see on the right-hand side here, I have a term a net x times delta t. And that reminds me of one of my other kinematics equations. So remember, a net x is equal to delta vx over delta t. When the acceleration is constant, the average acceleration is equal to the instantaneous acceleration. And so rearranging that equation, I just get a net x times delta t is equal to the change in velocity in the x direction, or delta vx. Okay, so now on the right-hand side of my equation, I have m times delta vx. We just learned that that's going to be the change in momentum. Specifically here, since I have velocity in the x direction, it's going to be the change in momentum in the x direction. And then we're going to define something new. We're going to define the impulse on the left-hand side. So F net x times delta t, we're going to say that this is the impulse. Specifically, it's the impulse in the x direction. So now I have a new relationship equating the impulse to the change in linear momentum, specifically in the x direction in both cases. Okay, so we already learned linear momentum is just p equals m times v, and that it's a vector pointing in the same direction as the velocity. Impulse, we just learned, is really the average force multiplied by the time over which that force is acting on an object. Okay, and really it's a vector. In the last example, we only thought about the x component, but really it should be a vector. And so if you think about it then, if you look at this equation, I'm multiplying by delta t, which is a scalar, so it's not going to change the direction of the impulse. And so then the impulse will be in the same direction as the average force applied to the object. All right. We also saw on that last slide that the change in momentum is related to this impulse. So here we go. We have the average force acting on an object is equal to the change in momentum over change in time. This is that new form of Newton's second law. And rearranging, we got that the impulse is equal to the average force multiplied by delta t, which is of course equal to delta p. Just looking at this first equation here. And so then I get that the impulse acting on an object is really equal to the change in that object's momentum. And so then a few more things we can say about impulse. It's a vector. It points in the direction of the average force acting on an object, or alternatively, looking at this second blue box here on the right-hand side, we see that it should be in the same direction as the change in momentum of the object. Okay, so that's sometimes a little bit harder to think about because it's a change in momentum. It's not the momentum at any given time. It's how that momentum direction is changing. And then it turns out that the average force multiplied by change in time, you can also calculate impulse as the area underneath a force versus time curve. So just like remember, work was F delta x, and then we calculated work as the area under a force versus displacement curve. And so I is F delta t, and so really I can be calculated as the area under a force versus time curve. Okay. And then what about units? So we already said that momentum has units of kilograms meters per second. And then we just came up with the relationship that I is equal to delta P. And so the right-hand side of that equation has units of momentum, kilograms meters per second. So the left-hand side must have the same units. In other words, impulse also has units of kilograms meters per second. Okay, so let's do an example of working with momentum and impulse. All right, so we have two balls that are dropped from the same height, and they both have some velocity v right before they hit the floor. So the first ball bounces right back up, but the second ball splats on the table and it doesn't bounce at all. And so we want to compare then the impulse given to the table by ball 1 to ball 2. Is ball 1 giving the greater impulse? Is ball 2 giving the greater impulse, or do they give the same impulse? Okay, so the trick to solving this one is to remember that impulse I is equal to change in momentum. And we have to think about the change in momentum of each of the two different balls. So the impulse delivered to the table is going to be equal to the change in momentum of the ball as it hits the table. Okay, so in case 1, we know that the initial velocity is really going to be v. That's the velocity right before it hits the table. And the final velocity, it's going to bounce back up off of the table. And so actually the final velocity as it bounces back up, it's going to be some value of v, but it's going to be going in the opposite direction as before. So the initial velocity is downwards. The final velocity is upwards. So if this is an elastic ball, like a really bouncy ball, then the velocity right after it hits the floor, the ball hits the floor, it should be the same magnitude but the opposite direction compared to right before it hits the floor. So if before we let the downwards direction be the negative direction and the upwards direction be the positive direction, then I get m times v for my final velocity minus m times minus v for my initial velocity, right? So if I let down be negative, my initial velocity would be negative. Okay, and so then the total impulse would be 2m times v. What about case 2? So this is the case where the ball splats on the table and so it doesn't bounce afterwards. Okay, so this is still the trick then. We have to think about the change in momentum. Just like ball 1, the velocity right before it hits the table is going to be minus v, right? Downwards, and it has some value v. And then right after it hits the table, the velocity is 0. It doesn't bounce. It splatters on the table. And so the final velocity of the ball is going to be 0. And so then I get 0 minus m times minus v, and so I get mv. And so that tells me that case 2 delivers a lower impulse than case 1. And so I would pick A here. Case 1 gives the greatest impulse to the table. And so now we want to think about the direction of the impulse. Is it going to be upwards or downwards? And this is specifically the impulse given to the ball by the table. Okay, so to answer this question, remember impulse has the same direction as the change in momentum, or it has the same direction as the applied force. So you can think about it either way here. So here I have the ball as it hits the table. I have time going to the right. And so as the ball hits the table, what happens is the table is going to push up on the ball, right? And so the impulse delivered to the ball should have a direction that's the same as the direction of the force that's applied to the ball, which is going to be upwards. Alternatively, you can think about the change in direction of the momentum of the ball. So remember we said it's going downwards to start with, and then it's going upwards afterwards. And so the change in velocity, the change in momentum is going to be positive. And so then again, we would get upwards for the direction of the impulse on the ball. And then the force exerted by the ball on the table is going to be in the opposite direction. It's going to be downwards, right? And so then the impulse delivered to the table is going to be equal in magnitude. The ball is touching the table for the same amount of the time that the table is touching the ball. And so they'll have equal magnitudes for the change in time. They also have equal magnitudes for the forces exerted because that's that Newton's third law pair. So the force exerted by the ball on the table is equal to the force exerted by the table on the ball. And so we end up getting the same impulse in magnitude but opposite directions. So the impulse on the table would be down. Okay, so now let's think a little bit more about this idea of impulse, where remember impulse is really equal to change in momentum, and it's also equal to the average force applied multiplied by the time frame over which that force is acting. So this becomes really important when we think about things that are like colliding or things that are getting jostled around and we want to minimize the force acting on an object. Think about minimizing that force, or to think about safety, is to use this equation that I have here, delta P equals F average times delta T. And the way that we can think about it is by noting that in some sort of collision, usually delta P is fixed. So a lot of the times, if you think, for example, about a car that's crashing into something, it will have some speed, initial speed, and so it will have some initial momentum, crashes into something, and then it will be stopped usually. And so then delta P is going to be fixed by the collision itself. We don't really have that much control over delta P. But what we can do is we can manipulate delta T, and by manipulating delta T, we can change the average force that acts on the object to cause a particular change in momentum. Okay, so let's take a closer look at what I mean by that. As I mentioned, this is used often to improve safety. Basically, the idea is that if you can increase delta T, then you would need a smaller F average to get the delta P that you're looking for here. And so you want a small force to minimize damage to an object in a collision. So this could be a car, it could be an object that's being shipped, it gets jostled around and you don't want it to break. And so the idea behind a lot of this safety and packaging material is really increasing delta T. So for example, if you think about a car in a collision, cars will tend to crumple. And so this has two effects. So the first thing is, remember back to those two balls that were dropped on the floor and the one bounced and the other one kind of splattered on the table. And remember we said that the impulse was smaller. So in other words, the force was going to be smaller when car coming to rest. Okay, and so that's like that splattering ball. Okay, so it gives us the minimum impulse. So that's a little bit here, but then the second piece is that the car takes a long time to crumple, and so as it crumples, that increases the time frame over which the force is acting, and it minimizes the force then acting on the car to cause the change in momentum. And by extension, then it minimizes the force that's acting on you during a collision. So that's why cars, even if maybe you tap something lightly, it will cause a big dent in your car. It's designed for your safety. Okay, this is also the idea behind gymnasts land on foam material. So again, it's as the foam compresses, it increases the time over which the change in momentum, the slowing down of the gymnast as they're landing happens. And so that decreases then the force exerted on their joints and hopefully helps prevent injuries. And then the same thing lastly with bubble wrap, it increases the time over which, the object that's being shook around inside that bubble wrap is getting hit. And so it decreases then the force acting on the object inside the bubble wrap as well. Okay, so let's do a quick example here. You drop one egg onto the floor and then another onto a foam or rubber pad, and it doesn't pounce. And we want to know which one has a greater impulse acting on it. Okay, so this goes back to this principle that the impulse is equal to the change in momentum. The first case, an egg dropping on the floor, it's probably going to smush on the floor. So I'm going to say that it's going from some initial velocity to 0 velocity. Okay, and then the other egg is dropped, and it drops onto a soft foam pad and it doesn't bounce, and so its final velocity is also 0, and so then the change in momentum of each egg would be the same, and in other words the impulse would be the same in both cases. So this would be C here. Okay, next piece of this question then is, in which case is the average force on the egg going to be bigger? Okay, so logically, we're going to expect that the force is bigger on the floor, because if the egg lands on the foam, it probably might not break. If it lands on the floor, it's going to break. So I would expect the answer to be the floor, but let's see why using physics. So remember, impulse is the same in both cases. And so impulse is going to be the average force times delta t, or in other words, we can solve and we get the average force is going to be the impulse or the change in momentum divided by delta t. So if the change in momentum or the impulse is the same in both cases, and delta t is going to be smaller for the case where the egg hits the floor, it takes less time for it to collide with the floor than for the foam, which will give a little and, kind of like move around and cushion it. It slows the impact. And so then we would get a greater force for the floor like we expect. Okay. And so it turns out that when we have collisions, momentum will end up being conserved. And so what I mean when I say conserved, just like when we talk about conservation of energy, this means that the quantity remains constant. So in other words, momentum is going to be constant in all directions. So it's going to be constant in the x direction, and it's going to be constant in the y direction. And so where does this come from? Well, starting with our Newton's second law, which we've rearranged as F net equals delta P over delta T, if the net force acting on an object or a system, so this would be the net external force acting on a system if you have more than one object in your system. An external force is really just meaning that it's something outside of what you have defined to be your system is acting on something inside the system. So we're going to do some examples with that, so don't worry. In general, we say the net force acting on an object or a system, the net external force is 0. Then you can see directly from Newton's second law that delta P over delta T must be 0. Multiplying both sides by delta T, we get delta P equals 0. And so delta P is really just P final minus P initial. So then rearranging, we get P final is equal to P initial, or in other words, the momentum must be constant, or we would also say conserved. Okay, and so then as I've noted here, these are vectors. P final and P initial are vectors. And so then both the magnitude and the direction, or in other words, the individual components of the momentum before and after a collision must be the same. And so this is a really useful problem-solving technique, and before we use it to solve a problem, we're going to see how we would have to solve a problem without it, and then we're going to look at how nice and easy it is to solve a problem with conservation of momentum. So first of all, here we have two skaters that are initially at rest. Skater 2 has twice the mass of skater 1, and we want to know what is the velocity of skater 2 in terms of the velocity of skater 1 after they push off. Okay, and they're told that they push off from each other with a force of 55 newtons that lasts 1 second. All right, and then the last question is also, what is the final momentum of the system? So in this older method of solving, we will have to think about kinematics and also Newton's second law. So let's get started with our knowns here. So first thing we know is that mass 1, skater 1, let's say has mass m1, and then we'll say, let's just call that m, and then m2 is double m1, so let's say that that's going to be 2m. Okay, and then we know that they are both initially at rest, so let's say v1 initial equals 0, v2 initial equals 0, and then we know the final velocity of skater 1. Let's call that, well, let's just leave it v1 final. All right, and then final velocity of skater 2, v2 final. This is the thing that we're looking for, and it's going to be in terms of v1 final. All right, we still have some more stuff that we know. So the force here, they're pushing off from each other with a force of 55 newtons. So what that tells me is that the force of skater 1 on skater 2 is equal and opposite to the force of skater 2 on skater 1. So they have the same magnitudes and they're both going to be 55 newtons, but they'll be equal magnitude opposite in direction because they're a Newton's third law pair. And then we know that this push lasts 1 second. So delta t is going to be 1 second. Okay, all right. And so how would we go about solving this problem? How would we find the final velocity? Well, we have to think about our good old Newton's laws and then also some kinematics. So if we were to think about the kinematics and the Newton's laws in this case, we could draw all of the forces acting on both skaters. So let's do our free body diagrams here. Let's do both of them. So we have free body diagram 1 and 2 for skater 1 and skater 2. So let's say skater 1 is on the left-hand side, skater 2 is on the right-hand side. Of course, they both have weight, so let's say this is going to be m1 times g, m2 times g, and then the normal force keeps them from falling through the floor, so this is going to be n1, n2. Okay, and then we know that skater 2 is going to push on skater 1, right? So that would be the last force acting on skater 1. It's going to be the push of skater 2. And the push of skater 2 is going to be, if they're positioned the way I have them drawn, it's going to be in the negative x direction. So this would be F of 2 on 1. All right. And then the force of skater 1 on skater 2 would be in the opposite direction. So it's going to be pushing to the right, and this is going to be F of 1 on 2. Okay. And then we know the magnitudes of those forces. So what we can do then is we can think about the net force on skater 1 and the net force on skater 2. Think about the acceleration, which will tell us about the velocities of those two skaters. So let's start with skater 1. Okay, so then F net, here since we're only really thinking about motion in the x direction, we're only concerned with net force acting in the x direction. So let's do F net x. It's going to be equal to the force of skater 2 acting on skater 1, which is going to be negative F of 2 on 1. And so that's all of the forces acting in the x direction. It's equal to the mass of skater 1 multiplied by the net acceleration of skater 1 in the x direction. And so this is going to be negative 55 newtons in the x direction. And so then I would say that A net in the x direction for skater 1 is really just going to be negative 55 newtons divided by m1, which I really called m here. Okay, so that's the net acceleration of skater 1. What about the velocity of skater 1, the final velocity? Well, we know that v final of skater 1 is equal to v initial of skater 1 plus A net. This is all in the x direction really. For skater 1 times t. So that was just one of our old kinematics equations for constant acceleration. And so what I can do is I know v1 initial is 0. That goes away. And so then finally we're left with V1 final is equal to A net x multiplied by t, so we can plug in A net x, and then t was 1 second. So we get minus 55 newtons divided by the mass of the skater times 1 second. Okay, so that's our V1 final. Now let's do the same thing for skater 2. Okay, so we can do the same thing. We only really care about motion in the x direction, so then let's look at the net force in the x direction. It's going to be equal to the force of 1 on 2. It's the only thing happening in the x direction. That's going to be the mass of skater 2 times the net acceleration in the x direction of skater 2. Okay, F1 on 2 is really 55 newtons. And then we know M2 is really M1 times 2. Okay, so this is really going to be 2M multiplied by A net x of skater 2. Okay, so let's solve for the net acceleration of skater 2 in the x direction. It's going to be equal to this 55 newtons divided by 2m. Okay, and so now we can solve for the final velocity of skater 2 the same way we did for skater 1. It's going to be V2 final equals V2 initial plus A net x 2 times delta t, the change in time over which the force is acting. So in other words, the time over which the acceleration is happening. Okay, and so then I can plug in my acceleration here, and I can also use the fact that the initial velocity is 0. And so I get 55 newtons divided by 2m, and then the amount of time is 1 second. Okay, and so now I recognize here I have 55 newtons divided by m times 1 second. So that looks a lot like V1 final over here, right? So it's negative V1 final. So in other words, my final result here is that V2 final is equal to minus 1/2 V1 final. Okay, so that was a lot of work. Wait until we see how to do it with conservation of momentum. It's so much easier. And so the last question here is, what is the final momentum of the system? I'm going to do it up top. Sorry, it's kind of messy. And so P final of the system is going to be equal to the momentum of each object inside the system. So here the two objects in our system are our two skaters. And so that's going to be M1 times V1 final plus M2 V2 final. And so then that's just going to be M times V1 final plus M2, which remember is 2M, times V2 final, which is minus 1/2 V1 final. Okay, and so then if you look at that, I see that I have these 2's that cancel, and so then I just get M times minus V1 final, and so my total final momentum is 0. Because my skaters were both initially at rest, the initial momentum was also 0 here. And so then you can see that P final is equal to P initial, and so we do have conservation of momentum. Okay, and that's going to be great because that helps us solve this much more easily. And so let's just take a closer look at this idea of internal versus external forces using that example that we just solved. So in that example, let's make our system be the two skaters. So that's how we did the final momentum. We said the system was the two skaters, and then we summed together the momentum of each one to get our final momentum of the system. So I have my free body diagrams for my two skaters here. And I've color-coded the forces. So internal forces are forces acting by objects in the system on objects in the system. So here our system are the two skaters, and so the internal forces are the Newton's third law pair forces, F2 on 1 and F1 on 2. So they're always going to sum to 0. And so whenever you think about the net force acting on a system, the internal forces will always sum to 0. You're always going to get these Newton third law pairs inside the system. So they'll never contribute to a net force. Okay, Then we have to think about external forces. So this is the key to knowing whether or not we can use conservation of momentum, is do the external forces acting on the system sum to zero? So in this case, we can see that we have the weight downwards of person 1. It will be perfectly balanced by the normal force acting on person 1. And so there's no external force, no net external force acting on person 1. Person 2, it's the same thing. The weight will be balanced by the normal force, and so there is no net external force acting on the system. So this means that the net internal plus external forces will be 0, and so we do expect to have conservation of momentum, which we did find at the end of that last problem. So how can we solve this problem with conservation of momentum? Well, first of all, we knew that they were initially at rest, so the total momentum of the system, so that's the sum of the momentum of each skater, is 0. Okay, then the final momentum must also be 0 if we have conservation of momentum. So we can use that to find the final velocity of the skater 2 in terms of the velocity of skater 1, because the final momentum is going to be m1 v1 final plus m2 v2 final. Then we remember that m2 is really 2 times m1, and then all we have to do is set it equal to our initial momentum, which was 0, and we can solve directly for v2 final. It's minus 1/2 v1 final. And that's it for this problem. So we get the idea here that conservation of momentum is very useful in problem solving. That's so much easier than going through all that work that we just did. Okay, so we'll want to use conservation of momentum. All right. So let's do a quick idea thought problem here. Is it possible for the total kinetic energy of the system to be non-zero when the total momentum is 0? And I'd be thinking about, what about the last problem? What did we just get in the last problem? What was the kinetic energy? Okay, so in that last problem, remember that we had some final velocity for our skaters that was non-zero for each skater. So remember, we found that v2 final was equal to minus v1 final divided by 2, right? And so then the total kinetic energy of the final kinetic energy of the system would be k1 final plus k2 final. Okay, and so that would be 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. That's going to be 1/2 m1 v1 final squared plus 1/2, remember m2 is really 2 times m1, and v2 final was really v1 final divided by 2, divided by -2 really, squared. And so when we add those two things together, because v2 final, it's negative v1 final divided by 2, but the squared means that it ends up giving us a positive kinetic energy, right? So we never get negative kinetic energies. And so really what we end up with here is 1/2 m1 v1 final squared plus another 2 of those. And so then we get 2, and we also have the 2 in the denominator that gets squared. So that ends up being a 4. And so I really end up with 1/2 plus 1/4 multiplied by m1 v1 final squared. And so really we get 3/4 m1 v1 final squared. And that is non-zero, even though we know that the final momentum of the system was 0. Okay, so I would say that yes, you can have a total kinetic energy that's not 0, even if the momentum is 0. All right, so just a quick summary then, we know these different definitions for impulse and change in momentum. And so if we have the external force, the sum of external forces acting on an object equal to 0, we know that the momentum of that object will be constant. If you have a system of objects, remember we want to add together the total momentum of each object in the system that you defined. And then if all the external forces acting on that system sum to 0, momentum will again be conserved, but we'll have to think about the total momentum. So the momentum of individual objects in the system can change, just like our skaters, their individual momenta has changed, but the total amount of momentum in the system will be conserved. Okay, and so then just a quick reminder again, momentum is a vector. That last problem, everything was happening in the x direction, and so we only had to think about the x direction, but in general, you'll have to think about both momentum in the x and y directions. Let's do one last practice problem here. If a ball is thrown to you with mass m and speed v, and you catch it, and then you also catch a ball with mass 2m that's thrown to you with speed v over 2, we want to know, is the sting that you feel in your hand, is it going to be greater for the first ball or the second ball? Okay, so really then the sting is going to be the force on your ball. So that's the same thing as like the egg splatting on the floor or like the car crumpling. So the force is really the thing that's giving you the sting. And so the greater the force, the greater the sting you're going to feel. And so we really want to think then about change in momentum and how that's related to force times change in time. So in case 1, the change in momentum is just going to be minus m times v, whereas in the second case, we get minus 2m times v divided by 2. So those 2's cancel, and we again get change in momentum of m times v. And so in either case, it's the same change in momentum. You get the same impulse, so then we get the same sting on your hand. Last piece of information for today, and we're really going to focus on this next time. As I mentioned, momentum and impulse is really useful in thinking about what happens during a collision. So in general, when we have collisions, we're going to want to think about before and afters. Just like when we did conservation of energy, we thought about like initial states and final states. Same thing with collisions. You'll always want to think about initial, which is right before the collision, and final, which is going to be right after the collision. So you'll think about the different objects that are colliding. You'll want to think about both their masses and velocities to calculate the initial and final momenta of the individual objects in the system. You sum them together to get a total initial momentum, sum them together to get a total final momentum, and as long as there's no net external force acting on the system, then you will get conservation of momentum in both the x and y directions. So then we'll just briefly mention that there are a few different types of collisions. And so we'll have to think about these different types of collisions when we think about how we can analyze the system. So no matter what type of collision you're talking about, if there's no external force acting on the system, which generally there won't be, then momentum will be conserved. But it turns out that kinetic energy is not always conserved. So in an elastic collision, this is when kinetic energy is conserved. So you can sum up the total kinetic energy before of each object in your system, set it equal to the total kinetic energy after the collision. If you have an inelastic collision, however, then the kinetic energy will not be conserved. And so you cannot set those two things, the kinetic energy before and after the collision, equal to each other. So how will you know if it's elastic versus inelastic? In an elastic collision, it will often say, like the problem will often say, it's perfectly elastic. And so that's a pretty good sign that it's going to be an elastic collision. In elastic collisions, a lot of the times they'll tell you that the objects stick together. So whenever you have objects that stick together, that tells you that it's an inelastic collision, and so then kinetic energy will not be conserved. These are also nice because that means that afterwards, after the collision, you'll really only have one object. If it's, two people stuck together, for example, then that one object will have a total mass that's equal to the sum of the individual masses. And then you'll also only have to solve for like one final velocity. So it's kind of nice when they stick together. And so then it turns out that if you have a one-dimensional collision, the speed of separation after the collision is the same as the speed of approach before the collision. And in 2 dimensions, we really have to think about conservation of momentum in both x and y directions. But we'll unpack those next time. That's it for today. I'm sorry it was a little long. There's a lot to do on momentum and impulse. So that's it, and I will see you in class.